There's a conversation happening right now inside the halls of some of the most prestigious scientific institutions on Earth, at the Paris Observatory, at the University of California, Santa Cruz, at NASA's Jet Propulsion Laboratory, and it is not the conversation the public is being invited to have. The official announcements speak of exciting findings and new insights into planetary science. The press releases use words like fascinating and unexpected. But underneath that carefully managed language, if you read the actual research, if you sit with the raw data coming out of the James Webb Space Telescope's observations of Pluto, a much more unsettling picture begins to emerge. This is not a story about a dwarf planet. This is a story about the limits of human knowledge, about a signal in the infrared spectrum that should not exist, and about what it means when the most powerful telescope ever built by human hands stares into the outer darkness of our solar system and comes back with an answer that nobody can explain. Let's go back to the beginning, because the beginning matters. For most of modern astronomical history, Pluto was a ghost. Discovered in 1930 by Clyde Tombaugh, it spent the better part of a century as nothing more than a faint dot of light at the very edge of telescopic resolution. Even the Hubble Space Telescope, as revolutionary as it was, could only resolve Pluto into a blurry smear of color and shadow. Scientists made educated guesses. They knew there was methane ice. They suspected nitrogen. They theorized about a thin atmosphere. But the data was thin, ambiguous, and always arriving through a fog of technical limitation. Pluto existed at the boundary of what human instruments could reach, and it seemed content to stay there, distant, cold, and silent. Then came New Horizons. In July of 2015, NASA's robotic spacecraft completed a 9-year, 3 billion-mile journey and flew past Pluto at nearly 31,000 miles per hour. The images it sent back were extraordinary. Mountains of water ice rising 2 miles above the surface, vast frozen plains of nitrogen ice so smooth they looked carved by an invisible hand, glaciers, dunes, a heart-shaped basin the size of Texas that became one of the most iconic images in the history of space exploration. But perhaps most shockingly, Pluto was not dead. It was geologically active, it had weather, it had a thin but real atmosphere, and wrapping that entire alien landscape, faint and almost invisible against the black of space, was a haze, a blue haze, layered, complex, stretching hundreds of miles above the surface. Scientists noted it, they cataloged it, and then, because New Horizons could not stop, it flew past Pluto and kept going into the darkness, they filed the haze away as something to be studied later, when better instruments became available. That later arrived in the form of the James Webb Space Telescope, and what it found has quietly rewritten everything. Here is what most people do not understand about the James Webb Telescope. It is not simply a bigger, better version of Hubble. It is a fundamentally different kind of instrument. Where Hubble sees primarily invisible light, the same light your eyes see, Webb operates in the infrared, detecting heat signatures and molecular fingerprints that are completely invisible to any telescope that came before it. Webb's primary mirror is 6.5 meters across, composed of 18 gold-plated hexagonal segments, and it sits at a point in space called L2, nearly 1 million miles from Earth, permanently shaded from the sun by a tennis court-sized sunshield. This is a machine designed specifically to see things that have never been seen before. And when it turned that machine toward Pluto, the data it produced was unlike anything that existed in the scientific record. The first major revelation came through Webb's MIRI instrument, the mid-infrared instrument, which operates at wavelengths between roughly 5 and 28 micrometers. At these wavelengths, Pluto does something that no other world in our solar system does. It glows, not visibly, not in any way you could see with your eyes, but in the mid-infrared spectrum, Pluto's haze emits a powerful thermal signature, and not from the surface below it, but from the haze itself. The haze is radiating energy. It is actively participating in Pluto's climate system in a way that fundamentally changes how scientists must model not just Pluto, but every haze-covered world in the outer solar system. The lead researcher on this discovery, astronomer Tanguy Bertrand of the Paris Observatory, described it as a discovery of major importance. And then he said something that should have made headlines everywhere, but was barely mentioned in mainstream coverage. He said, "It's a new kind of climate, unique in the solar system." Think about what that means. In the entire catalog of known worlds, 8 planets, dozens of major moons, hundreds of minor bodies, there's apparently nothing else like what Pluto is doing. Nothing. But here's where it gets significantly more complicated and more interesting. For years before Webb even launched, a scientist named Xi Zhang at the University of California, Santa Cruz had published a theoretical model suggesting that Pluto's haze would behave in exactly this way. That it would act as a cooling agent, simultaneously radiating energy outward into space while energizing molecules in the upper atmosphere, allowing them to escape. He published this prediction in 2017. Nobody could test it because no instrument was sensitive enough to detect the signal he was predicting. Then Webb launched. Then Webb turned toward Pluto, and the data that came back confirmed Zhang's model almost exactly. In planetary science, he said, it's not common to have a hypothesis confirmed so quickly within just a few years, so we feel pretty lucky and very excited. The confirmation of an 8-year-old theoretical prediction about the most remote object in the conventional solar system. A prediction that rewrites Pluto's climate from top to bottom. That is the first layer of what Webb found, but it is not the deepest layer, not even close. Because around the same time that the haze research was being finalized and published in Nature Astronomy in June 2025, another team of researchers was doing something slightly different. Instead of looking at Pluto's thermal emissions, they were examining its spectral fingerprint, the specific wavelengths of light that Pluto absorbs and reflects. This is how astronomers identify chemical compounds on distant worlds. Every molecule interacts with light in a unique, predictable way. Methane absorbs at specific wavelengths. Water ice absorbs at others. Carbon dioxide, ammonia, ethane. Each one leaves a distinct mark on the spectrum, like a fingerprint. Scientists have vast databases cataloging these fingerprints for thousands of compounds. When you point a spectrograph at a planet and take its spectrum, you compare what you see to what is in the database, and you identify what you're looking at. It is one of the most reliable tools in the entire arsenal of planetary science, and it works beautifully, until it does not. When the research team led by Bruno Bizarre of the Paris Observatory analyzed the James Webb spectra of both Pluto and Saturn's largest moon Titan, they found something that the database had no answer for. At precisely 511 micrometers, a very specific, very narrow range in the mid-infrared, there was an absorption signal, a dip in the spectrum where light was being absorbed by something on the surface. They cross-referenced it against every known molecular fingerprint in the published scientific literature. They compared it to hydrocarbons. They compared it to nitrates. They compared it to photochemical compounds known to form in atmospheres rich in methane and nitrogen. They compared it to every icy compound that could plausibly condense onto a frozen planetary surface in the outer solar system. Nothing matched. Read that again. Nothing matched. The James Webb Space Telescope detected a chemical signal on the surface of Pluto that does not correspond to any known molecule in any existing scientific database anywhere on Earth. This finding was uploaded to the scientific preprint server R-Archivo on June 11, 2026. As of this moment, it has not been formally published in a peer-reviewed journal. The identity of the compound responsible for this signal remains, officially, unknown. And this is where the story becomes genuinely extraordinary. Because Pluto is not the only place Webb found this signal. The exact same absorption at 511 micrometers, the same impossible fingerprint, was also detected on Titan. This should not be possible. Titan and Pluto are among the most different worlds you could choose to compare in the entire solar system. Titan orbits Saturn, roughly 886 million miles from the Sun. It is a large, warm by comparison moon with a dense nitrogen-methane atmosphere so thick that sunlight barely reaches the surface. It has liquid lakes of ethane and methane. It has river channels carved by hydrocarbon rain. It is one of the most complex and chemically active environments in the solar system. Pluto, by contrast, orbits the Sun at an average distance of nearly 3.7 billion miles. It is tiny, roughly two-thirds the size of Earth's moon. Its surface temperature is minus 375 degrees Fahrenheit. It is frozen, remote, and almost entirely lacking the kind of dynamic chemical processing that makes Titan so interesting. These two worlds share almost nothing except a broadly similar atmospheric composition, methane and nitrogen. And yet, the James Webb Space Telescope has detected what appears to be the same unknown molecule on both of their surfaces. The scientific team describes this coincidence as not one they can ignore. What makes this finding even more layered is that the signal is not identical on both worlds. It is present in both places, at the same wavelength, but its shape is different. On Titan, the absorption feature is relatively narrow, absorbing about 6 to 7% of incoming light at that wavelength. On Pluto, the same feature is roughly 3 times wider. That kind of asymmetry almost always points to an external source. It suggests that something is falling onto Titan's surface and accumulating preferentially on one side. Space is not empty. It is filled with charged particles, cosmic rays, and interplanetary material. The trailing hemisphere of a tidally locked moon tends to accumulate material that the leading hemisphere sweeps through and deflects. The implications of a surface molecule arriving from outside the moon itself are significant in ways that planetary scientists are only beginning to articulate. Now, some candidate compounds have been proposed. The research team has pointed to a class of molecules called alkenes, carbon chain compounds with specific structural properties, as potentially close to what could produce the observed signal. But here is the crucial word: close. The alkene candidates come close to matching the observed absorption, but they do not fully replicate it. The shape is not quite right. The width is not quite right. The team notes that systematic laboratory experiments are needed, that researchers must actually synthesize candidate molecules in laboratory conditions that simulate the extreme cold and radiation environment of Pluto's surface, and then test whether those synthesized compounds produce the signal that Webb is detecting. This work is underway. It has not been completed, and until it is completed, the identity of what Webb found on Pluto remains an open question with no satisfying answer. This is the reality that mainstream science coverage is not quite capturing. The narrative being offered to the public is one of incremental discovery. Exciting findings, new data, more research needed. The reality buried in the papers themselves is something considerably more profound. The most advanced telescope ever built by human civilization has detected a molecular signature on the surface of a world that should be one of the simplest, most frozen, most chemically inert places in the solar system. A signature that matches no known compound. A signature that inexplicably also appears on a completely different world, hundreds of millions of miles away. And nobody, not the Paris Observatory team, not NASA, not any research group on Earth, currently knows what that compound is or why it exists in both places. What most people are not seeing is that this is not a situation where scientists are slowly filling in the details of a picture they already understand. This is a situation where the picture itself has just been shown to be wrong. Let's place all of this into a broader context because the implications extend well beyond Pluto and Titan. The outer solar system, the vast region beyond Neptune where Pluto orbits, is home to thousands of icy bodies collectively known as Kuiper Belt objects. Pluto is simply the largest and most famous among them. These worlds are sometimes called remnants of the early solar system, chemically preserved fossils from the era when the planets were still forming, roughly 4.5 billion years ago. If the unknown molecule Webb detected on Pluto is an exotic compound formed through chemical processes, driven by cosmic radiation and extreme cold, it may be present on hundreds or thousands of other Kuiper Belt objects that we have never studied in detail. The chemical complexity of the outer solar system may be dramatically greater than current models account for. And if it is, that changes the fundamental story of how the building blocks of chemistry, and potentially biology, were distributed across the early solar system. Earth's water, Earth's organic chemistry, Earth's earliest prebiotic molecules, the origin of all of it may be tied to processes operating in the frozen outer reaches of the solar system, in ways that are only now becoming detectable. There's also the question of what this means for the search for life beyond Earth. The conventional framework for thinking about life in space is built around what scientists call the habitable zone, the narrow range of distances from a star where liquid water can exist on a planetary surface. Pluto sits so far beyond this zone that it has never seriously been considered a candidate for life. And yet, Webb's data is forcing a reconsideration of how complex chemistry can become even in the most extreme cold. Pluto's haze, it turns out, is not just a passive filter of sunlight, it is an active chemical factory. Organic compounds form within it. They rain down onto the surface. They are irradiated by cosmic rays and solar wind particles. They transform. The surface of Pluto is not simply frozen methane and nitrogen. It is a slow-motion chemical laboratory that has been running continuously for 4.5 billion years. When you extend that kind of chemical processing across billions of years, the question of what might be produced becomes genuinely open. According to informed sources in the planetary science community, the possibility that life, in some extreme or radically different form, could have existed outside the classical habitable zone of the solar system is no longer being dismissed with the certainty it once was. And then there is Charon. Webb did not only observe Pluto, it observed Pluto's largest moon in detail that was previously impossible. What it found there added yet another dimension to an already complex picture. Published in the journal Nature Communications in October of 2024, research using Webb's data detected two compounds on Charon's surface that tell a story of deep time. The first is carbon dioxide. This is not surprising in isolation. Carbon dioxide is common in the solar system. But on Charon, the carbon dioxide is preserved in a way that indicates it has been there since Charon's formation. Locked into the crystalline structure of ancient water ice that has never been warmed, never been processed, never been altered by geological activity. It is, in the most literal sense, original material from the birth of the solar system. The second compound is hydrogen peroxide. This is far more interesting. Hydrogen peroxide does not simply exist on icy surfaces in space. It is produced when water ice is bombarded by radiation, cosmic rays and energetic particles from the sun, that break apart water molecules and cause them to reassemble into hydrogen peroxide. Finding it on Charon tells researchers exactly which regions of the surface have been exposed to that radiation and for how long. It is a radiation dosimeter frozen into the chemistry of another world. Together, these compounds transform Charon from a passive, featureless moon into a geological and chemical archive. encoding within its surface a record of processes that have operated continuously for billions of years. The discovery, as one researcher put it, expands Charon's known compositional inventory in ways that open the possibility of further, even more surprising discoveries with future observations. The real story, connecting all of this together, is one that the scientific community is only beginning to fully articulate. Webb has revealed that Pluto is not the simple, frozen, dead world that the scientific consensus had long assumed it to be. It has a dynamic, haze-driven climate unlike anything else in the solar system. It has chemical compounds on its surface that match no known molecule. It has a moon that preserves a chemical record of the early solar system and shows evidence of ongoing radiation processing. And it sits at the heart of a vast, unexplored region of space filled with thousands of similar worlds that we have never looked at with instruments capable of revealing any of this. Every assumption that was built on decades of limited data must now be re-examined. Every model that was constructed without Webb's capability to distinguish Pluto from Charon, to separate their thermal signatures, to detect mid-infrared absorption features that previous instruments were simply too insensitive to see. Every single one of those models is now potentially incomplete. The implications for future missions are already being felt. Within the planetary science community, conversations about the feasibility of an orbital mission to Pluto, a spacecraft that would not simply fly past, but would slow down, enter orbit, and spend years studying the system in detail, have moved from the theoretical to the practical. A flyby is what New Horizons gave us. An orbiter would give us something fundamentally different. It would allow scientists to map the unknown molecule across Pluto's entire surface, to track seasonal changes in the haze, to watch Charon's chemistry evolve under radiation in real time. NASA's Dragonfly mission, currently scheduled for launch no earlier than 2028, will arrive at Titan sometime in the mid-2030s, and will be able to directly sample that moon surface chemistry, potentially identifying the unknown compound there. But Pluto, still further, still more remote, has no such mission currently planned. And so the answer to what Webb has found on Pluto's surface may not arrive for decades. The mystery compound at 511 micrometers will remain unidentified until laboratory experiments reproduce it, or until a spacecraft crosses 3 billion miles of vacuum and touches down on a world colder than the imagination. But what haunts the most careful reading of all this data is not just the unknown molecule, it is the pattern it reveals. Two worlds, separated by hundreds of millions of miles, sharing a chemical fingerprint that does not exist anywhere else in the known universe. A fingerprint that is not in any database, that has not been produced in any laboratory, that no model predicted, and that may have been there, waiting to be seen for 4.5 billion years, long before Earth's continents formed, long before life emerged in Earth's oceans, long before the first human eyes turned upward toward the sky and wondered what was out there. The James Webb Space Telescope was built to answer questions. It was built to see back to the beginning of the universe, to detect the atmospheres of planets orbiting other stars, to push the boundaries of what human instruments could observe to their absolute limit. And what nobody expected was that in looking outward to the most distant corners of the cosmos, it would also look inward at our own solar system and find something here, something close, something in our own backyard that we cannot explain. That is the thing about genuine discovery. It does not arrive with answers. It arrives with a signal at 511 micrometers, 3 times wider on Pluto than on Titan, matching nothing in any database, pointing toward a compound that no human laboratory has yet synthesized, waiting in the cold and the dark at the edge of the solar system. And the question that no one is quite answering, that the press releases are not addressing, that the headlines are not capturing, is this. If a molecule this significant, this widespread, this chemically persistent, has been hiding on the surface of Pluto for billions of years and we only just found it now, what else is out there that we have not looked at with the right instrument at the right wavelength? What else is the outer solar system holding, silently, in the dark? What if Pluto is not the exception? What if it is only the beginning of the discovery?